Will be recorded. Hello, everyone, and welcome to our media roundtable, Taming the Wild Mississippi River Delta. I'm Liza from the EGU Media Relations Office, and this session is meant to be an informal open discussion. So the scientists we have here will present some brief materials, and then you're all free to ask questions. And we'll invite you to use the raise your hand function that's down there at the bottom panel, or you can just wave your real hand at us. Please turn on your video and ask your question live, or if you're not comfortable with that, you can put it in the chat, and our moderator, Allison Sataki, will pose it to the panel on your behalf. On-site reporters will be able to meet with our on-site panelists, which is everyone this time, in the quiet room in RO5 following the roundtable. And we'll also have slides and additional materials available to you in the press information exchange on EGU Connect. I'll drop that link into the chat in a few minutes. Please bear with us should any technical issues arrive. As Zoom goes down for any reason, we'll switch to presenting via teleconference line. And if this happens, I'll immediately send you an email to all panelists and attendees with information on how to access that teleconference line. If you have any technical issues during this roundtable, please email news@agu.org, or you can drop a note to me in the chat. So now I'm going to turn it over to Allison Sataki from Louisiana State University to introduce all of our panelists and moderate the session. Go ahead, Allison.
Good afternoon. Thanks so much, Liza. We're really pleased to be here at AGU in New Orleans, and we're excited to present this research. This is going to be an informal discussion, and we have an update from our Mississippi River Delta experts. This is a AGU media roundtable called Taming the Wild Mississippi River Delta. And my name's Allison Satake. I work in the LSU Media Relations Department and the Office of Research and Economic Development. Today, you're joined by Dr. Jeffrey Obelcz. He's a marine geologist at the U.S. Naval Research Laboratory. And Dr. Kendall Valentine, a postdoctoral research associate at the Virginia Institute of Marine Science, College of William and Mary. And Dr. Samuel J. Bentley, the Billy and Ann Harrison Chair in Sedimentary Geology in the Department of Geology and Geophysics, and the Vice President of Research and Economic Development. Our scientists will give a brief update, followed by a moderated Q&A. Dr. Obelcz?
Okay. Thank you, Liza and Allison, for the introductions. So I'm Jeff Obelcz. I'm a marine geologist at the U.S. Naval Research Lab, and I'm also an LSU alumnus. So today we're going to be talking in various ways about the Mississippi River Delta being a wild system where we as humans have really tried in many ways to engineer and control the behavior of the river and the delta. And despite that, it continues to kind of just do its own thing. And we've been trying to do research in several ways to predict and study and parameterize how the river is moving and changing and how the delta is as well. So primarily what I'm going to be presenting and focusing on today is actually the part of the delta that you can't see. I'm going to be focusing on the subaqueous or submarine part of the Mississippi River Delta, which is approximately 0 to 300 feet below sea level. And the terrestrial part, or the part that we're all living and standing on right now in southern Louisiana, is the part that is perched on top of the subaqueous part. And this is in terms of size, you can think of the delta as more like an iceberg, where the terrestrial part of it is a very small amount of the total volume of the delta. So why we care about the part of the delta that we can't actually live or do things on is because there is a huge amount of infrastructure on the subaqueous part of the Mississippi River Delta, oil platforms, oil rigs, and we've been aware of, due to a number of accidents, oil rig topplings, pipeline breakages since the 1950s and 1960s, that the subaqueous delta is as dynamic as the terrestrial part of the delta, and is prone to geohazards, including mudflows and turbidity currents that can interfere with all this infrastructure that we've built on it. So what I'm going to be presenting today is, can we go to the next slide, Allison? A project, interagency project, with a large number of partners that are both federal as well as the National Academy of Sciences, and it will include private and university components as well. And this collaboration is called the Offshore Analysis of Seafloor Instability and Sediments, or OASIS. The goal of the project is to use a suite of recently developed techniques in seafloor mapping, sampling, direct observations, as well as numerical modeling to better understand where, when, and how large these seafloor instability events will happen in the northern Gulf of Mexico, but primarily on the subaqueous Mississippi River Delta front. And the need for a project like this arose when we realized that all these different agencies have mandates and needs to quantify these geohazards, and that it's a force multiplier for us to be able to work together between agencies if we're all trying to achieve the same goals to kind of predict the location and size of these geohazards. So the first tier of the research approach is going to be to map the entire subaqueous part of the Mississippi River Delta front for the first time since 1980s using modern high-resolution geophysical techniques such as multi-beam sonar as well as chirp sub-bottom profiling. This effort is built on a pilot study that started in 2014 with the Louisiana State University, the Bureau of Ocean Energy Management, and a couple other partners that identified key knowledge gaps in our understanding of the subaqueous Mississippi River Delta front. And one of those, first and foremost, was the fact that we don't actually know what the seafloor is shaped like in a large amount of the area. So this figure to the right is our plan for breaking up the MRDF into survey areas that will be surveyed over the next few years. We were planning to start this past September, which was delayed by COVID as well as Hurricane Ida, but hopefully we're going to be able to get out there starting in September of 2022. The next tier of the research approach for studying this is a comprehensive suite of seafloor sampling campaigns as well as in situ seafloor monitoring. So actually putting devices down on the seafloor that record how the seafloor moves that will complement the mapping effort that I discussed in the last slide. So the top right shows a piston core, which is a device that we use to recover sediment samples from the Mississippi River Delta front. This is from a cruise in 2017, and it's this in situ information that confirms information that we can get using seafloor mapping in much higher spatial resolution that we get from the mapping data, which provides full coverage. The lower figure is a device developed by the Monterey Bay Aquarium Research Institute to be placed on the seafloor, and it records the motion of the seafloor to provide a high resolution time series of how the seafloor moves. These devices were used in Monterey Canyon out offshore of California. We're developing similar devices to use on the Mississippi River Delta front. And finally, the third tier of the approach is going to be using recently developed probabilistic, primarily machine learning, as well as deterministic, which is numerical computer modeling techniques, to acknowledge the fact that we're never going to be able to directly observe everything at all times about the MRDF, so we need to be able to predict it in between. So this right panel that I'm showing is recent efforts at the NRL that we've done to take repeat multi-beam survey data. So those are the black lines in the figures, and those are really sparse transects of data that we have showing where we have coverage, and then we use machine learning techniques to interpolate or make the best computer educated guess about what the area looks like in between. So this just leverages a smaller amount of data to work smarter, not harder, to understand the system. And all these will be used through the OASIS project to learn more about the subaqueous Mississippi River Delta front. So with that, I will hand it over to our next panelist, Kendall, who's going to be talking about the terrestrial part of the Mississippi River Delta.
Thank you, Jeff. Thank you everyone for being here. My name is Kendall Valentine, and I research the terrestrial part of the Delta and focus specifically on kind of the smaller scale things that are going on in the Delta. So here is a picture of me in the field in Barataria Bay. And I spent a lot of time out here in my time in Louisiana, taking a look at the salt marshes and seeing how they're eroding and how we can best protect this really valuable coastal resource. And so one of the things I started to notice when I was out doing field surveys and measuring waves is that not all of these shorelines were eroding the same. And this is really important for when we're making coastal restoration efforts. And so what I was noticing is that northern shores and southern shores didn't seem to be eroding equally. And I went back to the lab and looked at maps and noticed that over, last 100 years, southern shores were eroding about twice as fast as northern shores. And so, maybe the wind was stronger from one direction, you were getting more waves. I went out, put out sensors and found that no, the waves are about the same. So how can we be getting such a drastic difference? And then I started maybe looking at some of the other very dominant, very visible things in the marsh, and that's plants. And as it turns out, when water levels are high, which is the more typical when waves hit the northern shore, those waves impact the plants. And the plants have roots that hold the sediment together and actively prevent erosion and dissipate wave energy. But on the southern shores, waves most commonly hit when the water level is very low and you're hitting mud that doesn't have any of that stabilization from the roots. And so you were getting a double erosion rate based on that water level. And so these plants are having a huge impact. And so I started to look, well, there's a lot of different types of plants within the marshes in Louisiana. They're not the same. So I was previously looking only in the salt marshes. So these are the very southernmost marshes. But then I started looking into the more northern marshes, or the brackish ones that have some more freshwater influence. And if you look, I have some pictures of plant roots here, and in the salt marsh, they're really big and they tend to be really strong and hold together, really actually hard to take samples. But in the brackish marsh, these roots tend to be finer and they can't provide that same kind of strength. And if we look over that same kind of 100-year time period, the brackish marsh is eroding twice as fast compared to the saline marsh. And this is particularly important for restoration, especially sediment diversions, where we're thinking about introducing fresh water into previously salty areas. So we need to think about the quality of land that we're building and how to best manage it based on these kind of qualities. I also noticed another really cool, interesting part of the system that a lot of people overlook. When you look at the surface of a marsh or a mudflat, even in your pond in your backyard, you might see this thin layer of kind of green-brown fuzz, pond scum. It's actually biofilms or microphytobenthos, and it's basically microbes and their secretions. And these secretions actually serve as a super glue and actively prevent erosion, similar to how plants function, but they can grow a lot faster. And I did a bunch of research showing that these guys can actually colonize the marsh really quickly and prevent erosion even up to hurricane force currents. And so this is kind of another overlooked thing that we might be able to use when we're building new land and making created marshes, because they provide rapid stabilization. So it kind of, even from the very small scale, this can make very large differences in delta-wide restoration. So now I'm going to pass it over to Sam, who's going to kind of synthesize both the terrestrial and the subaqueous part of the delta. Thank you.
Kendall.
Sorry about that, everybody. Yeah, I'll back it up. Actually, we can go to the first slide. You got to have one of these in every Zoom meeting, right? So river systems evolve through a balance of forces between sort of self-deterministic evolution of the river, sort of the erosion of banks and the natural migration of river channels back and forth, and also external forcing, things like floods, things like earthquakes, snowfall, and other sorts of forces like that. Geologists refer to the self-deterministic aspects as autogenic properties, and external forces are called allogenic. And over much of the last 200 years, humans have tried their best to curb the allogenic or the autogenic or self-deterministic characteristics of the Mississippi River by putting dams, by putting levees, by hardening the riverbanks. And this has allowed us to reduce flooding, but it's also had impacts on the extent of the lands associated with the delta. So here you can see the land loss that Kendall was just talking about between 1937 and 2000 in the in the lower Mississippi River Delta. We can go to the next slide. And one characteristic that not everybody understands about the Delta is that there's more than just one or two, even three outlets for the Mississippi River. There are actually dozens of outlets in the lower Delta. And these outlets are for the most part uncontrolled, and they're responding naturally in an autogenic fashion to sort of the balance of forces in the area. And this is one way in which the river still maintains some sort of self-deterministic characteristics. It still has some control of its own destiny. So let's go to the next slide. And a couple of examples of this are shown right here. And these are basically charts of sedimentation that's occurred since the 1960s in the Mississippi River. The upper panel encompasses essentially the Mississippi River from New Orleans south to close to the end of the river. And you can see that these numbers, these bar graphs, go from negative to positive from 1960s to the 2000s. What that tells us is that the river is sedimenting in the last couple of decades, where previously it had been erosional. So the river is changing its own behavior over time. The lower panel shows a similar pattern, this time looking at the downstream distribution of sedimentation. What we see is that from upstream near New Orleans to downstream near the mouth of the river, we have increasingly rapid sedimentation within the river channel over time. This is another example in which we try to control the river, but it's still maintaining some of its own destiny. Next slide, please. And in fact, this is actually happening offshore in the subaqueous portions that Jeff was just talking about. So this is a really interesting map that shows that each of the black lines here represents the location of the 30-meter water, or the 30-foot water depth at the year in which indicated on the figure. So from in 1760s to 1838 to 1867, the river was actually prograding in a seaward direction fairly rapidly in a fairly consistent direction. Then we get into the 20th century, the rate begins to slow down. And by the time we get to the end of the 20th century, the river, the Delta, is actually beginning to reverse direction. It's diminishing in size and it's shrinking. Geologists call this a Delta backstepping. So it's responding in ways that we really didn't know was happening. We've known about land loss, terrestrial land loss, for 100 years, but the first time we've learned about this degradation of the subaqueous portion of the Delta is just in the last couple of years. And in fact, if you look at every other of the main river outlets in the lower river, it's happening in these locations. Next slide, please. But it's not a simple story. This is a map that shows increases and decreases in water depth farther offshore from the Mississippi, from the outlets of the river. And as Jeff was suggesting, it's a very complicated pattern, and we don't really understand exactly what's going on, but we really need to, because this is essentially the foundation of the terrestrial delta in the same way that a household is a foundation. We worry a lot about the foundations of our houses, so we should worry a lot about the foundation of the delta. Next slide. So stepping back a little bit, there's a lot still, although we've been studying the Mississippi Delta for hundreds of years, it still remains terribly important, and there's a lot we don't know about it. It's the value of shipping going in and out of the Delta is about $300 million a day. It produces about 30 to 40% of the tonnage of fish caught in the lower 48 states. And it's a critical food source for exporting grains nationwide, and it's also a big portion of our energy infrastructure. So it seems to me that this should be a national priority for us. We've invested billions of dollars in the restoration of the Everglades, which is, of course, a jewel in the crown of our national parks and of our wetland ecosystems. And it just seems to me that we should do the same thing for the Delta, maybe for different reasons, but it is incredibly valuable, and I think it deserves our attention as a nation. So, thanks, guys.
Great. And now we're going to actually open it up to questions. And I actually had a question for you, Dr. Bentley. This wonderful slide here that showed the how things were changing. What was happening in the early 20th century that warranted this change?
I'll unmute. That's a real. During the first half of the 20th century, the Bureau of Reclamation and other federal agencies invested a lot of money in flood control and water control in the upper tributaries that feed the lower Mississippi River. And so these are basically dams that cut off the sediment supply. For example, all the sediment coming out of the Rocky Mountains down to the Mississippi River. And this, So this is an example of how something that we were doing in Montana and Wyoming, in the Dakotas, actually created a really demonstrable impact down here in the Delta. And it was not unpredicted, but it's quite pronounced.
Great, thanks for providing that context. And Liza just put in the chat a little reminder that, inviting you to turn on your camera if you'd like to join the conversation with these experts, and you can either raise your hand. Michael, thanks for coming.
Second person to talk with me and on. I'm Mike Phillips, a reporter with the Associated Press.
Michael, I see. Oh, sorry, go ahead.
Okay. You mentioned the tributaries and the like that it effectively acted as dams where debris, sediment is not flowing downriver. Can you talk about just how much of an issue the dredging of fill material in those rivers that just is in a cycle contributes to this problem versus other kinds of flood control?
So are you referring to dredging in the upstream reaches, like up in the Missouri River?
Yes, exactly. Up in the Missouri, that's right. Yep.
Well, there's I can't comment directly on dredging activities in the Missouri per se, but the river is actually, since we put in dams, there are places where the river is actually scoured out extensively. So it's an example of where the river is responding to a human change in ways that sort of, in some cases, actually deepening. So, but I wish I had a good answer for you on the upper Mississippi dredging activities. In the downstream areas, particularly near the mouth of the Mississippi, it's gotten particularly intense, and it costs hundreds of millions of dollars over the course of, well, the dredging is continuous effectively for the Corps of Engineers in the lower Delta right now. So.
I had a question also for Dr. Valentine. Can you tell us a little bit about why the smaller scale may matter in such this vast region, and when we are also talking about land loss at such a huge, massive scale?
Yeah, great. Thanks, Allison. I think there's two main reasons. One is, when you're working in these communities, a lot of the people who are asking, they're saying, my house is this many feet from the water. How long do I have for my house, or how can we save my house? And so these small scale changes to the doubling in erosion rate will make a big difference in how long it takes for that given property to experience the land loss. And so, designing specific infrastructure to help prevent land loss that targets the specific process. So if you're having that, the waves hitting that very erodible material, we can prevent that specifically. But I think on the broader scale is that we can use these small scale processes to, you multiply that by the tens of thousands of kilometers of marsh that we have across the Delta, and then it actually turns out to not be so small scale.
Just as a follow-up, were you surprised by what you found when you investigated a little further into the erosion that was happening?
I was really surprised. I really thought the physical processes would be dominant, and I was actually not looking for the plants to be the major role. And I think perhaps maybe one of the most surprising things is when I started this work in 2015. By the time I finished the projects up in 2020, the land that I had originally worked on was gone, and so I think that was pretty striking. And that has really spurred me to continue working on these problems to try to stop land loss. Really.
We have a question from Liz Payton. Liz, feel free to open your camera. We'd love to see you too if you feel comfortable.
Okay, there we go. Yeah, so my question is for Jeffrey Obelcz, and that he was talking about the hazards in the seafloor, and that being part of the justification for needing to map the subaqueous part. And so I was wondering if you could talk about the hazards a little bit. Thank you.
Yeah, absolutely. I think the hazards to the seafloor can best be expressed in two events. One of which was in 1969, Hurricane Camille overtopped an oil platform, and more recently, I believe it was in the 2000s, a platform owned by Taylor Energy was toppled by a mudflow as well. So the commonality of these two events, both of which caused huge damage to energy infrastructure, and in the case of the Taylor Energy platform, started an oil spill that has continued for over a decade, is these platforms are really built and engineered to withstand hurricane force winds and waves. But when they were built, especially the ones that were affected by Hurricane Camille, they weren't actually considering that the seafloor that they're driving the pilings into could move, and are especially prone to move when the waves affect the seafloor. So it's not the direct action of the waves against the oil platforms, but rather the movement of the seafloor underneath the waves, as well as other forcings, even smaller events such as cold fronts that happen every year that can affect all this infrastructure. So with the combination of dramatic events such as that, as well as the fact that this movement of these mudflows on the seafloor are not uniform, are far from uniform across the entire Mississippi River Delta front, really spurs the need to know when, where, and how large the mudflows and other geohazards on the subaqueous Mississippi River Delta front are going to happen.
Great, thank you.
Michael, you have your hand raised. Go ahead.
Yeah, appreciate it. Sorry if I'm jumping in ahead of people here. What you just said, do we have any idea how many similar kinds of rigs or the like might be susceptible to those kinds of flows?
I would say that we have a generalized idea, but unfortunately right now, that map that Sam showed of the whole subaqueous part of the Mississippi River Delta front and change that's happened over it, it's more or less a big broad zone. We're saying if you're building pipelines or rigs, or in the case of the green economy, which is starting to be up and coming, obviously, maybe stuff like wind energy offshore, that this is an area you have to worry about. So it's good to know just that general broad information. But obviously, if you're a company considering siting new infrastructure in the Mississippi River Delta front, it would be really valuable to say that in a given year, there's a 1% chance of having a major seafloor movement incident that could affect the infrastructure, or a 10% chance, obviously. And that's the need to go from just this general, there's danger all here, to a quantified risk. And that's what we're trying to do.
Could I step in here? This is an area where I've actually done some research along with Jeff, and not focusing so much on the science, but on the cost. It's a matter of public record that the Taylor Energy platform has, let's see, I guess there's been about $500 million expended to date, and another $500 million encumbered to clean up clean up the Taylor Energy platform, and it's not done yet. And with respect to your question, I mean, I don't know exactly how many platforms are out there, but it's actually, if it's not a challenging effort to take a Bureau of Ocean Energy management map of platform locations and overlay to the mudflow hazard zone to identify ones that might be in the hazard. But so you're talking, in any case, you're talking about $1 billion of platform of risk exposure for an incomplete cleanup. So the as well as hundreds of kilometers of pipelines that crisscross this area. So this is not a new problem. This is something that Bureau of Ocean Energy Management has known about for a long time, and they've been concerned about it. And this is the OASIS effort that Jeff is working on is trying to bring this risk assessment and risk management into the 21st century from the 1970s.
Great. Thanks, Dr. Bentley. Do our panelists have any questions for each other? I know you work in separate areas, but all along in a very dynamic, interesting place.
I have a question for Kendall. Do you think that, so our research, a lot of times as researchers, we can kind of get tunnel vision on our specific problems, but one of the things that I really love about the AGU fall meeting is it's an opportunity to see science from well outside my field. So Kendall, having heard about the subaqueous part of the Mississippi River Delta, do you think there are maybe any lessons that you've learned working in the terrestrial area that might be able to be applied to the subaqueous?
Oh, thanks, Jeff, for that one. I think we have a lot more tools than we had when we were starting with the terrestrial delta. So I think that's one big improvement, that you guys will have a lot more information. I think, you know, a lot of snap decisions were made for restoration in Louisiana, or for management of the river. So, you know, in response to significant floods, we had a lot of levying of the river and things like that. And we didn't have as much information and as much science. And so I think going into managing the subaqueous delta is, you know, gathering as much information as possible, using the state-of-the-art tools, and then kind of being able to make a very well-informed decision. I think that's what our advantage is at this point.
Thanks, Kendall.
We have another question from Liz. Go ahead, Liz.
Yeah, and my question is really probably not answerable, but can you talk about the changes that are sort of man-made because of all the dams and trying to control the river versus the climate change impacts to the river and the delta?
I'll take a first swing at that if you guys are okay. I think at the present time, at this exact point in time, we may not have a good idea of what we may not be able to filter out climate change impacts on the Mississippi River or the Mississippi River Delta right now. That said, what I have read, and again, it's not my area of research, but it's just sort of reading the literature, is that there are likely to be some profound impacts, both to the river basin itself and also to the subaerial and subaqueous portions of the delta because of climate change. A couple of quick examples. There's a lot of uncertainty about what we think it's going to happen to rainfall patterns over the next 100 years, but some of the scenarios include basically the same amount of water is going to fall on the river, but it's going to fall at different times of the year. So we have higher highs and lower lows in terms of floods. That's going to change the power distribution of the river, and it's going to change how sediment deposits and how sediment is eroded from the river channel, potentially in some pretty remarkable ways. Another aspect is that hurricanes are major sculpting agents on the coastal regions of Louisiana and like any other coastline. And we are even now beginning to understand that a changing climate is going to bring different types of hurricanes at different frequencies. We're expecting to see more large, powerful storms, which can cause much more of the damage that Jeff was talking about, and also be much more powerful agents of change for the coastal areas that Kendall is working. So that's coming. I don't think we have it nailed down exactly what it's going to look like, but it's definitely coming down the pike.
Thank you.
I have a little bit more to add. When I was talking about, the waves impacting at different water levels on those plants, that's actually from the passage of cold fronts. And I know with climate change, we're kind of expecting kind of intensification of weather patterns. So with this more dramatic changes, we might actually have more action of having waves hitting beneath the plants. And so that might actually enhance erosion within the terrestrial delta as well.
I have a question, Dr. Valentine and Dr. Obelcz. You both had mentioned in your your comments about the tools and technology has advanced to be able to look at your specific areas. What tools or what technology do you find like the most helpful in coming to the conclusions that you've had? That maybe weren't possible before?
I can go first. So the main tools that I use, there's some really old ones and some really new ones. So I do a lot of field work where I look at the actual sediment cores, and that's, digging up plants, digging up the sediment. And those are not new technologies, but I use that information to develop large scale models. And so we can kind of use the power of, actually being in the field. And then, you can only be in one place at one time in the field, but you can bring that information into a model and kind of simulate everywhere at all times. So I think, computational power has made that possible. A lot of the models I developed can run on a laptop, so that's something that, 30 years ago would absolutely not have been possible. So we can make much better predictions and, try a lot of different scenarios for restoration.
Yeah, and to piggyback on that, Kendall, I would also agree that computer modeling has been the primary advance specifically for us at the U.S. Naval Research Lab. So for us, we as an agency to provide the best information for our war fleet, as a scientist, saying I don't know is an acceptable answer. For the Navy, as a scientist, saying I don't know isn't good enough. So we have to provide a best estimate. And in that case, using machine learning, which can learn about a data set and then provide a best estimate of what a parameter can be somewhere it can't be measured, is really critical for when we're working in denied areas, strategically denied areas, which obviously does not at all apply to research that I'm doing on the Mississippi River Delta front. But obviously, in a system, in a world where we have finite time, money, and resources to study these things, machine learning can still be used as a force multiplier to collect a small amount of data and make inferences over a broader area based off that data, like I showed with the repeat survey mapping. So I would second Kendall's assertion that modeling has definitely been a real key in improving our understanding of the natural systems.
And Michael, I see that you have another question for our panel.
Thank you. This one's for Professor Valentine. I hope I'm pronouncing that right. The modeling that you use, has it revealed any new types of landscape that might be more at risk than you initially thought? Based on your work, anything that surprised you about the near future?
Yeah, so I mean, one of the big things was that difference between saline and brackish marshes. So for all of our model projections, not just in Louisiana, but across estuaries worldwide, we kind of treat all the marshes the same. We don't really think about saline or brackish marshes in terms of modeling that differently. So when I was doing the work and kind of implementing some of those plant root processes, the model indicated I was really making kind of big mistakes in the brackish areas. And so I was like, well, how can I make this model better? When the field kind of noticed those plant root characteristics. And so that model illuminated a place that we had a major gap in our knowledge and allowed us to kind of develop new modeling techniques to be able to get kind of estuarine-wide scale predictions. Did that, if you want me to elaborate, please push me along.
No, that got at most of it. I didn't know if there was, just when you look at a map, if you realize that there was a certain area that was all of a sudden much more vulnerable than you realized, so.
Yeah, I think so. One of the things is, like, if you look at some of these maps, actually, Allison, can you pull up those maps? I think I have some in the background. If you give a second, but if you look at the maps, there's going to be kind of blue is the water, dark blue is land, and then yellow will be the land loss between like the 1850s and present. And so this is kind of looking at these maps gave me a lot of ideas. We're having some, give us 1 second. It's okay, Allison. But I think, one of the striking things was that there was systematic differences between the North and South Shore, and just, it lights up yellow as you go farther north. I think you'll see this in a second. But you can kind of, 1 second. But I think, like, here we go. I don't want to do, so this is an insight into Bay Jimmy, which is in Barataria Bay. It was actually one of the places that was most impacted by the Deepwater Horizon's oil spill. So that's why I was working there. But like you can see, so the yellow is the land loss between 1877 and 2017. And so you can really see that those southern shores, there's a lot more erosion than you would expect. I would have expected within this small little micro bay. So, it's only about a half a mile across. You would really think that those marshes should be very similar. They're all the same plant species. It's all pretty much the same elevation. So I think seeing that dramatic of a change within such a small area. And then the next slide, Allison, we're going to zoom out, and this is all of Barataria Bay, and all those red arrows indicate where there's a difference between the North and South Shore. And then you'll also notice as you go way farther north, there's like a lot of like blotchy yellow spaces, and that's just like increased erosion happening within the brackish and fresher marshes. That's just not behaving how we would normally model it. So that I think looking at the feedbacks between, like, looking at the maps in the fieldwork and then applying that to the model is really a good way to be able to get at these problems.
Great, thank you.
I guess I have I guess Liz and Michael, do you have any other follow-up questions? If not, I have a sort of a philosophical wrap-up question for our experts. What do you see as the role of Louisiana and Mississippi River Delta front, this region? Why does it matter, especially looking at the global scale? Whoever would like to take this. I guess I'm looking at you, or do you? You each can take a turn.
Go ahead. Yeah, I guess I'll start with that one. In the global scale, one of the categories that the Mississippi River Delta gets lumped into is something called a megadelta, which is, I don't know the exact precise definition of one, but the Ganges Brahmaputra River Delta is another one. And they're just areas where there's an enormous amount of population, infrastructure, and just general societal value centered on them. So I think that a lot of these lessons that we learn about these deltas are translational between them, even though there are obviously differences and kind of unique behaviors to each of them. That just generally speaking, if we want to place it in the global context, is that the Mississippi River Delta is probably the most well-studied megadelta in the world, and whatever cutting-edge research that we can deploy here are lessons that can be deployed elsewhere on other really heavily populated river deltas worldwide.
And I'll jump in on that, is that I think Louisiana and working on the Mississippi Delta, we've really led the charge on developing restoration plans. A lot of global restoration plans have been based on the Coastal Louisiana Master Plan. And so we're developing the top science here in the Mississippi River Delta that hopefully, like Jeff said, will be applied elsewhere. So hopefully we're just kind of almost the canary in the coal mine of warning everyone of what is coming next and how to prepare.
And I'll follow up. I agree 100% with what Jeff and Kendall just said. We need to remember that probably 1 in 10 humans on the face of the earth either live on or near a coastal river delta. So that's a big portion of the population. An even larger portion of the Earth's population lives, generally speaking, in the coastal zone. And so you're talking there about 30 or 40% of the global population. And Kendall used the term canary in a coal mine. And this comes back to a question that we had from Michelle just, I guess it's from Liz just a few minutes ago. And she was asking about the impacts of climate change. Just because of the circumstances of the Mississippi River Delta, the reduced sediment load and the changes to the river itself that humans have caused have produced damaging coastal change in the Mississippi Delta. It's not caused by climate change, but it's the kind of change that will be caused elsewhere in the world by climate change in coming decades. So this is a living laboratory for the future coast worldwide. And in that sense, it's absolutely a canary in a coal mine. It's a test bed for new technologies, just like Kendall said. And it's also valuable to us. I mean, worldwide, coastal river deltas are enormously valuable in terms of food production, in terms of navigation, in terms of transport, in terms of energy infrastructure. So we need to get the message out. They're disappearing. They're incredibly valuable. And we need to restore, conserve what we can, and be able to plan for a retreat for places where we can't maintain a line in the sand. So it's an existential threat for many hundreds of millions of people worldwide. So.
Great. Thank you for those thoughts. I'm dropping my contact info into the chat, and if there are no other questions, I think we'll turn it back over to Liza, the AGU, and for your ongoing reporting, Michael and Liz, please feel free to reach out to us. And don't forget us down here in Louisiana in the Mississippi River Delta. Liza?
Right, big thank you to Allison, Kendall, Sam, and Jeffrey for bringing us this panel here today. That's going to conclude our media roundtable. We'll be back tomorrow at 9 a.m. Central Time with a briefing on rising heat in a changing climate. It'll be followed by another briefing on intensifying storms in a changing climate at 11. So we hope you'll join us for future press events. Have a great evening, and thank you for coming.